Here we go, it's the 2009 VCAA Specialist Maths Exam 1. We're going to look at now the solutions. Alright, so first thing here in question 1, find all the solutions of this equation. You've got z to the power 4 minus z squared minus 6, and that equals 0. Complex numbers. Okay, so what we have to recognize is that it's trinomial, and so because it's like a quadratic equation, we're going to perform this little substitution and we express it in as a quadratic, and we can get solutions for u. So u is equal to minus 2 and u is equal to 3. Now we have to remember that u is equal to z squared, so let's make that substitution again, and we take the square root of both results. And we have to remember we've got both the positive and the negative square root, and the square root of the negative 2 gives you the I as your imaginary unit there. Okay, so 1, 2, 3, 4 solutions for a polynomial to degree 4. So question 2 looks at a 50 kilogram student stands in a lift which accelerates downwards at a rate of 2 meters per second squared. Find the reaction of the lift floor on the student correct to the nearest Newton. So this reaction of the lift floor on the student, well, that's referring to the normal reaction force. So if we draw our little student in the lift, you've got the normal reaction force, there it is, vertically upwards, N, and you've got the student's weight force, 50 G's, vertically downwards. And it's important to identify the direction. Up will be positive, down will be negative. So we always start with Newton's second law, sum of forces equal to mass times acceleration. So we add our forces together, and recognizing that the acceleration is downwards, we have to make sure we've got a negative value for our acceleration, so negative 2. And we can solve for n, and we get 390 newtons. So an important thing here, how do we do 50 multiplied by 9.8? Well, you can think of 50 as 100 divided by 2, lots of 9.8, and multiplying by hundreds are easy, but then now we're just halving 980 to get 490. Okay, so that's a little multiplication strategy for exam 1. Now the next question, now the lift is accelerating upwards, okay, at a rate of 2 meters per second. So again, we're finding the normal reaction force of the lift floor on the students correct to during the second stage of the motion. So use Newton's second law, sum of all forces is equal to mass times acceleration. This time accelerating upwards, so it must have a positive 2 for the acceleration, and we can solve for n. And there's a little multiplication strategy, and we get 490 plus 100, 590 newtons. Okay, question 3. Let's resolve two vectors, this vector, into two vector components. So we're going to resolve this vector into components. Its components are one that is parallel to a second vector, and the other component is perpendicular to the second vector. So we call these the vector resolutes. One in the direction or parallel to this vector, and the other vector resolute that is perpendicular. So to find, first off, let's label this vector A and vector B. To get the parallel component of vector A is given by this expression. So this is an important one to remember. Dot product between A and B hat. Now B hat is your unit vector. And then dot product again with B hat. So here we go. That's the first bit, the dot product. Now we're dividing by the modulus of vector B squared, because we've got two unit vectors, B hat, and so we're dividing by two factors of the modulus. Okay, that's why we've got the modulus squared. Simplifying that, there's the dot product. We go the 5 times the negative 2 plus the 1 times the negative 2 plus the 3 times the 1. And we get our numerator there. This becomes a scalar, which is just negative 1, and we multiply the negative 1. And this vector there is parallel to our b vector. Now, to get the perpendicular component, we have to start with vector A, and we subtract the parallel component of vector A. And that's a vector sum to give us the third vector, the perpendicular component. Okay, so we use the result, what we just obtained, for the parallel component vector, this one. And we obtain this as in doing a simple vector addition and subtraction. Okay. Next question, question 4. Given that cos of 2 theta is equal to 3/4, where we have theta is some angle in the second quadrant, so you've got to think about sine and cos, whether it's plus or minus in the second quadrant. And our job is to find cis theta. Now, you've got to remember the definition of cis. Cis is cos theta plus I times sine theta. We've got to express that in Cartesian form. That's the x plus the yi form. Okay, so first thing to recognize is we've got cos of a double angle. So let's think about using a double angle formula for cos. Here it is, rearranging double angle formula for cos gives you an expression for single angle, cos of x, or should be cos of theta, pertaining to the problem. Okay, so let's now substitute our value in. So the cos 2 theta here in the formula, we're going to replace it with that value. And we have to remember that because it's theta is an angle in the second quadrant and cos is negative in the second quadrant, so we're going to use the negative sign in front of the square root. Substituting our 3/4 in, there it is, we've got the square root of 7/8, and we rearrange that third, and that's the best way to represent that third. Square root 14 on 4. Okay, so we've got cos of the angle. Now, we also got to work out sine of the angle to get the cis form. So the sine of the angle can be worked out using trig identity. This one, sine squared plus cos squared is equal to 1. Rearranging that for sine squared to get sine of the angle. There it is. Now, theta is, the angle theta is in the second quadrant, and sine is positive in the second quadrant, so we're going to use the positive sign here. Let's substitute our value for cos theta. That's what we worked out. Okay, and evaluate to get the result for sine theta. Perfect. It's a positive root 2 on 4. So we've got cos of the angle and we've got sine of the angle, and we're going to put those two values together in cis form. Okay, fantastic, and there we have it. That's the cis theta represented in Cartesian form. Okay, let's look at question 5. Consider the family of curves defined by the relation given here. K, the parameter k is just some real number. So part A, we have to verify that every curve in the family passes through this point, 0, 4. Okay, and we're going to do that by, to verify that a point is on a curve, we do that by substitution. And then we've got to find other points of intersect with the y-axis. So, got to remember, from the point you've got x equals 0, y equals 4, and points on the y-axis, well, that occur when x is 0. So there's the little substitutions we're going to be doing. Okay. So substitute those values into the relation first. And when we simplify, we get a negative 16 plus 20 is equal to the right-hand side, which is 4. That's correct. So we verify. That's just by demonstrating that the left-hand side is equivalent to the right-hand side. Okay, next bit, let's find another point of intersect with the y-axis, and that occurs when x is 0. So we substitute x is 0 into the relation, and it simplifies and it gives you this little quadratic in terms of y. So we're going to solve for y. Factorize, find the two factors, the two double brackets that multiply. Okay, and there's a solution for y. So these are the y values when x is 0. So the one value that's already given to us is 0, 4. Well, that's this solution. So the other point of intersection with the y-axis has to be this one, when y is 1. There it is. Okay, the next bit, find the expression for dy dx. So we've got our relation, and we're going to differentiate the relation on both sides of the equal sign. Okay, this is implicit differentiation. So differentiating each term, and carefully remembering that for the minus 2xy here, you have to use a product rule type approach when differentiating. And when you've got functions of y like y squared, you've got to use a chain rule differentiation. Okay, now we've got our dy dx as denoted as a y dash. So we're going to solve for y dash. So factorize common factor of y dash, and then divide by the bracket. There's our expression. Okay. Now, the next part is, it says, hence evaluate the gradient of the curve at this point 1, 1. So we've got our derivative function, our gradient function. So now let's evaluate our gradient function at that point. So again, we're substituting x equals 1, y equals 1. We're going to substitute that into our gradient function. Now, we get this in terms of k, because we haven't worked out parameter k yet. We don't know what that is. Now, if the curve exists on this point, 1, 1, then we can use that information. This is a solid point of information that fits with our relation, our curve, and we're going to use that now to work out what parameter k should be. So substitute the coordinates of the point back into the relation. And from that, we're able to solve for k. And we get k is equal to -1. Okay, so now we can substitute that into our result for our gradient. And there we go, dy dx at the point 1, 1 is a -6. Now question 6, this is a differential equation. Find all real values of m such that our solution, e to the power of mx, is a solution of our differential equation. So we can first do this through a process of substitution by verifying that our equation given to us is a solution to the dE. So we need to work out the dy dx, the first derivative, and we need to work out the second derivative. So the first derivative, these derivatives are easy. You're just multiplying the coefficient of x at the front of the exponential number. Now, let's substitute them into the dE. There we have it. And as you can see, the e to the power of mx is a common factor in each term, so let's factorize. And you get a quadratic as the bracket. So from this, we've got two parts. We've got e to the power of mx multiplied by the bracket, and that is equal to 0. So we use our null factor theorem, and we see that, hey, it can only be the quadratic equation that equals 0, because the exponential function never equals 0. It's asymptotic along the line y equals 0. So from that we can factorize and get solutions for m. And there's the two real values for m. Hi team, we're looking at Specialist Maths 2009, Exam 1 question. This question we're going to do all by ourselves, no cas. A mass has an acceleration given by that function v squared minus 3. V is velocity of some mass when it has a displacement of x meters from the origin. So let's go ahead and find v in terms of t, some function of v as a function of x. and we've got some initial condition there, right there, which we'll draw on to work out our integration constant c. So let's go about and see what happens. First, we're going to set up our differential equation using a in this form. Okay, v times dv dx. Now that's a useful form to use. Why do we use that one? Well, it's because in our information we've got our initial condition in terms of v and x, and our function for acceleration is in terms of v. There is no t variable, so there's no need to introduce it. Okay, now keep going. We rearrange our differential equation, okay, bringing all the v's to the left hand side and the x's to the right hand side, and then we integrate on both sides. Okay, now what we have to do there, before we continue on with the red, we have to make sure we have on this line, I've gone ahead and put a 2 in the numerator, and I've balanced that out with a half out the front. Why did I do that? Well, if I look at the integral, this one here, I have some quadratic in the denominator and a linear in your numerator, and so I remember something about that form. It's like the derivative over the function, and that is an important integral rule that gives me log of the function of x. Okay, so I'm going to draw on that information to integrate the left hand side. So off I go, integrate left hand side, modulus of v squared minus 3 gives us my integral, and I must include my c parameter, which I'm interested in working out. So I'm going to rearrange the equation to get c by itself, and then let's take our initial condition, let's sub it into the equation, and let's solve for c. C gives us just 1. Why does c give us 1? Well, what do we know about log of 1? Log of 1 is a value of 0. So if all that there is 0, then we just get c is equal to 1. Okay, let's state our function of x in terms of v, and now we have to transpose for v in terms of x. So off we go. We're going to first do the first part. Now this bit here, what did I do? I subtracted 1 on both sides, and then I multiplied by 2 to end up with this expression. Then I take the exponential of both sides, okay, to undo the log and end up with e to the 2x take 2. Take out a factor of 2, and here we'll factorize a little bit, and I've added 3 there. Then I'm ready to do a square root, and I have to remember to have a positive and negative. Okay, but hang on, that's kind of like 2 functions. I really just need one function, one unique solution. So which one's it going to be, positive version or the negative version? Well, coming back to the initial condition, look here, this is a little information telling us that v has to equal to negative 2 when x is 1. So considering the initial condition, we must have v as the negative version of that square root. Okay, alright, so very important, and something that we... Okay, question 8. Show that this function of x can be written in this form. Okay, so first off, you can see we've got a rational function. Polynomial divided polynomial. So let's do a division of polynomials. And from this division of polynomials, you'll see that a negative x squared divides into a positive x squared with a quotient of negative 1. And we multiply that through the divisor, and we end up with a remainder of 6 after we subtract our partial product, and we get a remainder of 6. So from that, our function of x can be expressed in this form: quotient plus the remainder divided by the divisor. And there we have it. We've verified that it can be expressed like so. Now our job is to find the exact area enclosed by the graph of this function with the y-axis and the lines x equals -1 and x equals +1. So it's a bound region that's described here. Okay, so as you can see, this area is found by this definite integral from lower limit of -1 to an upper limit of +1. Okay, where this rational function is expressed from part A, okay, in this form. That's the better form to integrate. So from that, you've got two parts. We've got the integral of the -1, okay, that's this part here. I've just taken the negative out. And we've got the integral of this rational function here, the simple form. And the 4 minus x squared, well, using difference of two squares, there's a double brackets there, x minus 2 times x plus 2. Okay, now from that it's also important to realize that this is symmetrical about the y-axis. It's equivalent on either side. So this integral from -1 to +1, well, that's also twice the area from 0 to 1. And this is an easier way to evaluate the integral. And as you can see, I've already gone ahead and integrated the constant number 1 here. Now, what we have here is integration by partial fractions. So our little rational function, we're going to pull it out and resolve it into partial fractions. So our numerator is given by this. Okay, now from these partial fractions here, we get these two simultaneous equations. These are easy ones to solve. A is equal to b from the first equation, and so that gives us a 2a plus 2a is equal to 1. So obviously then a is equal to b, which is 1/4. Alright, so let's use that. This 1/4 turns the 12 factor into a 3. So we've got this integral now. And the integral of these reciprocal functions, 1 over 2 subtract x, goes to a log. Okay, and I've got a subtraction of logs because this here has a factor of -1 out the front of the log when we integrate, and that subtraction of a log of 2 minus x becomes a division of the 2 minus x inside the argument of one single log. Okay, so now let's evaluate this from 0 to 1. And we end up with this part here, log of 1, which is a value of 0. So simply it's 3 times log of 3 subtract 2. And there it is as our result in exact form. Question 9. Now let's solve this differential equation with this initial condition, and we're going to determine a function of y, get a function of y as a function of x. So let's do that. Okay, now it's important to recognize the whole right hand side is a single function of y. So we're going to divide by this whole right hand side and bring it over to the left and have it as the reciprocal of this right hand side. There we have it. And integrating both sides, okay, gives us on the left hand side now this integral. Now it's important to be able to recognize the structure. Okay, so what kind of structure do you think this integral is going to give us? where we've got something squared plus something squared in the denominator. This is an arctan integral, that's correct. So we've got our factor for half arctan, and inside is our y plus 2 divide 2 is equal to an x plus c. There's the integration constant. So to work out what that integration constant plus c is, we got to use our initial condition, what's given up here. So let's do that substitution. And arctan of the number 1 is a pi on 4. Very important to remember. So we've got half of pi on 4 gives you a pi on 8 as your c value. Okay, so put that in. There it is. And now let's transpose 4y. So we get a tan function. Y is equal to 2 tan of 2x plus pi on 4 subtract 2. Fantastic. Now part B is using Euler's method to get an approximate solution for y1. Now this is a step of 0.1 away from x equals 0 when y is 0, our initial condition. So there's our formula for Euler's approximation. Okay, so to work out for y1, we got y0, and we've got the function when x is 0. Okay, and it's also, when x is 0, it's also the equivalent to when y is 0, and that's what we get from part A, from the initial condition. When x is 0, y is 0. Because our dy dx function is in fact a function of y, we can use that when y is 0 value. So we can evaluate that by substituting a y equals 0 from our initial condition into our function of y for dy dx. We get a value of 8. So this, using those values, substitute into Euler's method. There it is, 0 plus 0.1 times 8 gives you a 0.8 as your value for approximation. Alright, next question. Make sure you pause at the appropriate times to be able to work on this carefully. Alright, now question 10 gets us, we've got some function here, inverse sine function, and we have to, what is the domain and range? So the domain and range for basic inverse sine is stated on the formula sheet. It's important to look that up. The implied domain for just the basic inverse sine of x goes from -1 to 1. Okay, so that's the starting point. Now, the argument of the arc sine function, which is this part, the half x plus 1, well, that has an implied domain of -1 to 1. Okay, so we set that up like so, and now let's start to solve this just for x. Okay, so got a half x minus a plus 1, so I'm going to subtract 1 both sides, like so, to both parts of the inequation to eliminate this part here, to get that. Next part, I want to multiply by 2 on both sides to just get x by itself. So multiplying by 2 on both sides like that, and I end up with this as my domain, my implied domain. Okay, and you might be worthwhile to finish that off by writing something along the lines of x goes from -4 to 0. Oh, 0. There we go. And now, having found that, let's go get our implied range. Implied range for the inverse sine of x ranges from there we go. Implied range is negative pi on 2 to pi on 2. Okay, they're the corresponding values from negative 1 to 1. So, having a look at the function, if this part here, the arc sine, goes from negative pi on 2 to positive pi on 2, but then the function is multiplied by this amplitude, 2 over pi, and then subtracted 3. So I got to do those two operations to my minimum number in the range and the maximum number in the range, like this. Get the idea? Okay, now let's just simplify that up and we get a range of negative 4 to negative 2. Okay, and that's our value. Very nice. Part B says let's go ahead and find the derivative of that and express our answer in this form. So off we go. Let's differentiate our function of x. Write that out. Now I need to first see, well, there we go. I'm drawing on the rule for the derivative of the inverse sine. Okay, now that comes from this rule, which is on your formula sheet. Okay, that's your basic rule for the derivative of an inverse sine function. And by substituting the parts in the right spot, I get the right rule. And now expand the denominator and simplify. And let's take out the factor of negative x, because that is the type of form we are after. See, there's the factor of net x there, and we get that as our final expression, and that's in the right form, okay, as stated from the question. So a must have a value of 2, and b is a negative 1, and c is a 4. Okay, well, there you go, guys. I hope that's helpful, and all the best for your exam.